We're going to learn about unit generators. Unit generators are the basic building blocks of sound in Nyquist and actually in almost every uh, language or system for computer music. We'll look at what is a unit generator, some unit generators in Nyquist. We'll talk a little about the implementation, some concepts of functional programming. We'll get into a basic synthesis method, which is wavetable synthesis. And then we'll switch from the synthesis side to the more compositional and score side by looking at how to represent scores in Nyquist and how to manipulate scores. So we've got a lot of things to do that will enable you to actually start making music with Nyquist. So first of all, what is a unit generator? Well, in the 50s, Max Mathews, who is pictured here on the right, Max conceived of sound synthesis by software using networks of modules called unit generators. Unit generators are, in a sense, primitives, the basic building blocks in a sound synthesis system, and they perform sound generation and sound processing. Here are some examples of unit generators. These are the classic symbols that were introduced by Max many years ago. The oscillator has input controls of amplitude and frequency and has an output, which is sound. The multiplier takes two sounds as input and outputs the product of those sounds, sample by sample. And the envelope unit generator has a number of parameters that control the shape of a contour, and it outputs that contour. These are just typical examples. And the great thing about unit generators is they can be combined. So you start with simple unit generator behaviors and you patch them together and you build very complex synthesis algorithms. So for example, this is a classic kind of table lookup synthesizer. We have a wavetable at the upper left, which has amplitude and frequency controls. We have an envelope to shape the envelope or the amplitude of that oscillator output, and we do that by multiplying the two signals together. So now we have three unit generators that build a simple kind of synthesizer. Now, unit generators in Nyquist are represented as functions. So here's the relationship between the graphic unit generator diagrams and the functional notation of Nyquist. On the left, we have unit generators A and B, and A feeds into B, and there's some extra parameters X, Y, and Z. Okay, and so over on the right, you see that A is a function call with parameters X and Y, and the output of A, this whole expression, is the first input parameter to B, just like over in this diagram. We have A going into B. Okay, here is A as a parameter to B. And the other parameter, Z, is the second parameter to this function call on B. And B, of course, returns a value, which is this output value of the two unit generators. So here are some basic unit generators in Nyquist. The oscillator, or OSC, produces a sinusoid output at a given frequency. The PWL unit generator stands for piecewise linear. That means it produces a function which is a straight line between breakpoints, and that can be used to generate various control shapes. And here's a typical thing to do. If you multiply an oscillator by a control shape, you get envelope control. If you multiply two oscillators together, you get amplitude modulation of a different kind that we'll talk about. And so just a word about evaluation of these functions. Normally, SAL expressions evaluate their parameters first and then apply the function. So this is the way that most programming languages work. You evaluate the parameters first, you pass those values into the functions. But what about sounds? If we did this with sounds, we would be evaluating these parameters, A and B, which might generate gigantic sounds that we would have to store in memory. And only after they were fully computed could we invoke the function f on those sounds. To avoid storing these huge values in memory, Nyquist uses a technique called lazy evaluation. What that means is that samples are only computed when they are needed. And so Nyquist sounds either contain samples because they've been evaluated, or they contain the potential to deliver samples. In other words, they're in this lazy evaluation state where they haven't been actually computed yet, or sounds can even have a combination of some computed samples and some things remaining to be computed in the future. So just going back to this f of AB, if A was a Nyquist sound and B was a Nyquist sound, they could be very small representations of things to be computed in the future. And they can actually be passed into a unit generator F. Unit generators have the ability to hang on to these future values, these to be evaluated sounds, and only when we actually play F or we demand samples from F does F go in and ask A for samples, ask B for samples, use those samples to compute some output and deliver it. And so all this computation can be done incrementally. It's very fast and very efficient, and that makes Nyquist quite possibly the fastest synthesis system there is. It's a combination of deferring work until you absolutely need to do it, and then when you actually need to do it, doing it in a very efficient way.